So thank you, Xavier. So for the ones who doesn't know me, I am Abderrahmane ADEL. Today I will talk about my a part of my PhD work thesis. So this work is named Time Domain System Identification using fractional models from non-zero initial condition application to the identification of lithium-ion batteries. This work is supervised by Professor Olivier Brea and Professor Rachid Marti, the most known one here. So, the famous one.
Who is that guy? The second one.
So, c'est enregistré. So for this presentation, I will start by talking about the batteries and the fractional model. So I will talk the problematic of this work and then I will move to the system identification. The two methods developed here. The first method, two-stage algorithm, and the second method, output error with non-zero initial conditions. And I will finish my presentation with a conclusion and talk about the future work. So for the introduction, the lithium-ion batteries is an electrochemical element which is used in a lot of fields, going from mobile phone to aerospace and military equipment. The component of the lithium-ion batteries is two electrodes, which is inside a liquid called electrolyte, and there is separation between the two electrodes. And the battery have an external electrical circuit. So the working principle is based on two oxidation and reduction reactions that happens on the two electrodes. In the case of the discharge, the ions go through the electrolyte from the negative electrode to the positive electrode, and the electrons go through the external electrical circuits. And in the case of the charge, the same reaction happens, but the transfer goes from the positive electrode to the negative electrode. And the most apparent electrochemical phenomena that happens inside the batteries are the electric and ionic conduction, the double layer and transfer charge, the diffusion, and the aging. And this phenomena happens at different time response. In this work, we will not take into account the aging because the experimentation we did doesn't happen on a long time, so the phenomenon of the aging doesn't influence our work. So for the fractional model, the battery, there is different type of model for the batteries. On our work, we decided to use an equivalent circuit model based on the Thevenin model, and this different impedance used in this equivalent circuit model characterize different phenomena that happens inside the batteries. For the battery ohmic behavior, we use a resistance R0 and an impedance to characterize an impedance ZCT to characterize the phenomena of charge transfer and double layer, and an impedance ZD to characterize the phenomena of the impedance. And the frequency response of the batteries are plotted in a Nyquist diagram, a little bit different from the Nyquist diagram. This type of diagram is used in electrochemical field. They plot the negative part, the negative imaginary part of the impedance versus the real part of the impedance. As shown in this graphic, as you can see, the different phenomena happens at different frequencies. For the high frequencies, the most apparent phenomena is the battery ohmic phenomena, and in the middle, for the middle frequencies, the most apparent phenomena are the charge transfer and double layer, and for the diffusion, it's apparent in the low frequencies. And generally, the diffusion is characterized by the Warburg impedance, which is one of the solution of the Fick laws. So, to model the different phenomena in better way, we choose to use two CPUs. One CPU in parallel with resistance to characterize the phenomena of charge transfer and double layer, and another CPU to characterize the diffusion. If you don't know, the CPU is an electrochemical component, which means a constant phase element, and it characterized the formula shown here. It's as you can see, it's a fractional integrator. We have as an order alpha and a coefficient q. For the Warburg impedance, it's a CPU, but we have an order of 0.5.
It's a CPE.
CPE, sorry.
Because I was looking, where is the CPU?
It's a CPE. Oh, sorry, French and English. So to get function transfer of the batteries from the global impedance model, we choose to have a relationship between the different parameters of the model and the transfer function. So these parameters have a one-to-one relation. And the fractional models, if you don't know them, are models used to model a complex system with a long-term memory as thermal systems, electrochemical systems, and biology systems. And one of the problematic of the fractional models are the initial conditions. So there is different approach for these initial conditions. One of approach are Capoto approach, who considers all the paths of the system is constant, and there is two other approaches. One of Lorenzo and Hartley, we use the historic initialization function, and another one from Trijasu and Mamari, which is based on the infinite dimensional state vector of the fractional integrators. And there is paper between these authors who prove that both approaches have the same results, provide the same results. So the difference between a rational system and a fractional system, in the case of the rational system, the initial conditions are estimated along with the parameter, the system parameters. And for example, for a system of order one, estimates two parameters and one initial conditions. And also the free response decays exponentially. But in the case of fractional systems, the initial condition depends on the whole path of the system, and the system decays polynomially. So our problem which started this work is that one of the techniques used to characterize the battery is electrochemical impedance spectroscopy, which use as an input current or voltage, and as output they measure the output. From this data, we compute the impedance. And the necessary point for this technique, it's necessary that the battery should be relaxed in an equilibrium state. And for that, after charge or discharge of the battery, it's necessary to let the battery rest or relax. After that, we use the spectroscopy G for galvanostatic that use as an input the current and the output the voltage. So for our work, we used case of charge, and we let the battery rest for 30 minutes, and we applied the electrochemical impedance spectroscopy for one state of charge, one level of the state of charge. But for our work, we needed to have the characterization for different state of charge, and we did that. But the problem here, the experimentation, the duration of the experimentation, it was around 18 hours. So it's a long duration. So we thought about ideas to reduce or eliminate the relaxation time during the data acquisition, and we decided to use a technique based on time domain identification. So the system identification, the direct response of the battery after charge, we have a global response, and inside this global response, we have two responses: the free response and the forced response. So we thought about we needed to separate the forced response and the free response from the global response, and to apply an output error method to estimate the different parameters of the systems. So the output error identification is is the minimization of the quadratic error criterion. The quadratic error criterion is the difference between the response of the system and the model, and we using an Liebenberg-Marquardt algorithm, which is implemented inside the Alice-Moulin function optimization toolbox in MATLAB. So the first method developed is a two-stage algorithm. In this two-stage algorithm, this algorithm takes as an input the historical input data, the input data, and the output data. So firstly, in the first stage, the algorithm determines the free response from the global response and compute the forced response. And after this, the second stage, the algorithm identifies the different parameters of our model. So we use this two-stage algorithm on different examples. Here, for this example, we decided to use as an input pseudo-random binary signal with a step of current with current for charge and discharge. And before that, we did discharge time, and applied to a model of the battery we choose. After the output of this model, we use a white noise signal to white noise signal with a SNR of 20 decibel. The results we obtained are shown in the second graphic. So from this second graphic, we consider that the model structure is known, and we know the output, which is corrected by Gaussian white noise. We know the historical input data and the future input data. And for this, here we use a Monte Carlo simulation with 50 runs with the parameter standard deviation of the initialization model around 0.1 around the real parameters. And this, and the simulation are carried out for different relaxation time, to 60, 10, and 0 minutes. So the objective here is to estimate the free and the forced response, and from this results to estimate different parameters using the output error model. So the results we had from this. So the results we had from this simulation is shown here in this slide. As you can see, the different identified output for model for the 15 models are they fit perfectly the true output for the time response and also for the frequency response. And also the same we had the same results for different time relaxation for 10 and 0 minutes with a little bit difference between them, and the results we obtained are shown in this this table. As you can see, the algorithm converge the two-stage algorithm converge the true values of the parameters. So after that, we did the same simulation, but for now it's the parameter standard deviation of the intelligence model are around one of the real parameters. So it's the same. We have the same objective, and for this standard deviation, as you can see, the algorithm doesn't converge for every models. From every initialization model. So it's the same for the different time relaxation. And in this table, as you can see, we did the algorithm doesn't converge for all the parameters. This is why we needed to develop another technique, which is based on algorithms that converge, because the two-stage algorithm doesn't have proof of convergence. So yes, and after that we tried to apply this algorithm on real data. This real data we got them from an experimentation using the same input as in the simulation. As you can see here, the outputs are for different time response, and in the blue and the curve in the blue, it's the relaxation time of the battery. So after that, the hypothesis of this experimentation that we know the structure of the model, we know the historical input and future input, and we know that the battery is in state of charge of level 18%, and the experimentation was done on temperature chamber equal to 25 degrees Celsius. So the objective is to estimate different response, and from the results obtained to estimate different model and compare the results of the different relaxation times. Here for the results are shown in this table. We consider that for a time relaxation of 60 minutes are the closest to the true values, and as you can see here, for time relaxation of 30 and 10 minutes, the algorithm converge, but doesn't converge for a time of relaxation of 5 and 0 minutes. So, for the second method, it's based on the output error with taking into account the non-zero initial conditions. Here, the difference between this technique and the first technique is that we compute the free and the first response in the same time as we minimize the quadrant error. So the two responses are computed in this are estimated in the same time as the parameter model parameters. So we use the same simulation example, and here we directly use standard deviation of the initialization model 1 around the real parameters, and it was the same condition for the two simulation. So for this method, we got the better results, and as you can see, the different model fit perfectly the true values. For different time relaxation. So here, in the same results are shown here in the table. This results prove that this algorithm converge to the true values of the parameters. And we applied the algorithm for the same data used in the precedent example. And for this algorithm, the algorithm converged to the different the true values of the true values of our model, our battery, but we still have some problem with relaxation of 0. So yeah, we still need some time here. So to conclude to conclude our work, we presented a fractional order equivalent circuit model which characterized the state and the static and the dynamic behavior of lithium-ion batteries, and presented two different techniques to reduce the measurement time. And the difference between the two techniques, that the second method works better than the first method, but we still need to work on the two methods to improve them and get better results. So thank you for your attention.
Thank you, Abderrahmane. Questions?
Well, I didn't understand, how do you distinguish free response and forced response? Because you access only to, you have the output, not the output voltage variation, and you're setting an input excitation current. That's right.
Mm-hmm.
Show for example.
The examples.
Okay. Yes, here, for example.
Yes.
So you are using an excitation with a high frequency, with a PRBS, with a high frequency PRBS, in order to be able to estimate correctly the charge transfer.
The
constant, yes. And then the other one is you have a low excitation in order to be able to identify better the diffusion impedance. That's right.
Yes.
So you come in this both excitation.
Yes.
So, and how do you? I don't understand how you can distinguish free response and forced response, because you have both when you are measuring them.
Yes.
Then how do you because I understood that you first estimate the free response and then you use it to, or I didn't understand.
So for the first algorithm, we use the past input that we know that the battery was discharged or charged before the application. So we know the past input, and from the past input so we model the free response, and from the free response we compute the forced response.
But to model the free response, you need a model. So the question is how do you get
the model, it's the same as the battery model.
Can you speak about the first technique and then the second one?
Yeah.
Can you go back to the algorithm on the first technique?
So here, firstly, the algorithm takes as input the historical input data, the future input data, the PRBS and the signal to charge and discharge, and also the output data. So from the output data and the historical data, we determine the free response.
So can I add something?
Yes.
So first of all, you initialize the model. So
Yes,
So you initialize a model.
Yeah.
So from the initialized model, you can get the free response.
Okay.
Even though it's
I
wrong,
understand.
it's underestimation.
Yes.
You get the free response.
Okay.
So if you have that free response, then you get the forced response, and then at the end of the first iteration, you work on the forced response.
Okay.
Then you get another model.
Because you could
start again.
Because you could wait. For example, you could wait to have steady state,
Yeah,
steady state point, and then we can avoid using that. But the advantage is that you can start
directly
at any time, even if you are not at steady state.
Yeah.
The advantage of your method is
Yeah.
that yeah, that's
This is the first method. Maybe he can try to explain the second one.
For the second one, we use the same technique, but here
Maybe you can show the other algorithm.
sorry. So here in the second method, it's the same as the first method, but here we estimate the free response in the same time as the parameters.
okay.
So it's shorter. It takes plus de temps, a smaller time. So and the advantage of this technique is it uses the output error, and this type of algorithm have proofs of convergence. This is the difference between the first and the second method.
So when you're starting from a steady state, for example,
Yeah.
so you won't have any response.
Yes.
And so
It's
only
only
also it's not you don't need this method. I
No,
understand.
no, this is not the point. I mean, he doesn't assume that it starts from a steady state.
Yes,
We are assuming that we are charging the battery and we want to start immediately after.
yes, I understand now. This is the advantage of the method.
And in here, you just assume that your free response is a convolution product between your model and the fast output. Forced response is convolution of your model with the new input signal, and at the same time you are computing parameters of the same model, which appears at two places.
Okay.
Of course, things are much simpler in integer case.
Yes, of course, because you have
Because
only one.
First order, you have one parameter, so you can compute it in least
estimate
squares.
the initial.
But in fractional systems, the future depends on the whole past,
Yeah,
so the problem is difficult.
Yeah.
So guys, this is an unpublished work, so
okay.
keep it for yourself.
It's on the cloud, so
You need to censor it.
A question about your final results. Can you show us,
First or second method?
with the second
The
method?
estimation of the tables.
Simulation or practical?
Practical one.
Yeah.
Yeah. You have shown us that at 0 you have a problem.
Yes, we still have problems.
And at 5 minutes after, it looks quite good.
Yes.
And between 0 and 5, did you try?
No, we didn't try it. So yes, we don't. For now, the limit is 5 time work session of 5 minutes, and so our objective is to eliminate the time work session. So we work directly on 0 minutes. But yes, we think about doing it between 0 and 5 minutes. Yeah.
I hope.
I mean, for his supervisors, this is not satisfactory result. So
Yeah.
why doesn't it work at 0 minutes? Even if he initializes with the, I mean, even in simulation, when he initializes with the right model, I mean, it must work.
Yeah.
So still maybe have little problems in the algorithm. So we are checking this out right now.
You can just go back to the simulation rest. Yeah. There is noise. No, I don't remember.
Simulation.
There is noise.
Sorry?
Simulation. Yeah.
In the simulation?
There is
Yeah,
noise
noise.
or not?
Is it
Sorry?
Noise.
Ah, yes, there is no. Yes, there is a noise of 20 decibels.
it's only one realization.
No, it's 50 realization, but yes, for only one, yes. But here, what we tried to show is that it depends on the initialization. And we tried the simulation, and we had the same results for different noise. So this is why we tried to show for this presentation. We tried to show that the problematic is the initialization mode between the two methods. The difference between them, it's the initialization mode. As you saw in the first method, for a standard deviation of 0.1, it works, but for 1, it doesn't work. This is the difference between them.
Which means in the first method, you have to initialize very, very close to the true system to get it to work. That's why you asked Abderrahmane to make some Monte Carlo simulations by changing the initial points of the algorithm.
Okay. Thank you, Abderrahmane.
Thank you.